Hello everyone. In our group, we arranged a way in the first step to arrange a Claerbout III for two-way waves. So my colleague Chao will show you the recent progress and the very encouraging results this afternoon. But before that, let's first take a look at the Claerbout III for one-way wave, that is the Stolt migration, and compare this the Claerbout III for one-way wave with other migration methods. And I will take you through two different comparisons. And in the first comparison, I will make a comparison for Claerbout III for one-way wave and this asymptotic approximation, that is a Kirchhoff migration. And in the next comparison, in the second comparison, which is I will discuss this afternoon, that is I will compare two different imaging conditions, that is Claerbout II and Claerbout III for one-way waves. And in the end, I'll say the benefit of Claerbout III, that Claerbout III and Claerbout II are different imaging conditions. And Claerbout III can provide a physical experiment at depth with source and the receiver location at depth, and provide definitiveness and meaningful amplitude that other migration methods cannot provide. Okay. First, I will take you this slide shows where this talk fits in this processing tree. And in the first comparison, I will make a comparison between Stolt migration, which is Claerbout III for one-way wave, and Kirchhoff migration, and then retrieve the angle-dependent reflection coefficient from these two migration methods. This slide shows the migration method for Stolt migration and Kirchhoff migration. The first equation for Stolt migration, which is Claerbout III for one-way wave, we first take a Fourier transform of the data from space-time domain to wave number frequency domain, and then we use the Stolt migration formula here. Will give us the Stolt migration image. And Kirchhoff migration, which shows the formula is shown here. This Kirchhoff migration is a asymptotic approximation of the Stolt migration. And however, the asymptotic approximation, Kirchhoff migration, loses the ability to predict the source and receiver experiment at depth. And they are discussing and Kirchhoff migration loses the ability to predict the source and receiver experiment at depth, and it loses the definitiveness, and whenever the image at depth will give you the information. And there are analysis and numerical tests for the asymptotic approximation that is from Stolt migration to Kirchhoff migration. And my colleague Chao and Jing and Qiang al. has discussion for this topic. I'm not going to take you through this all the detail for this topic. There is a review in the annual report, and I'm glad to discuss with you about this topic. First, let's see how can we retrieve the angle-dependent reflection coefficient from Stolt migration. And the first equation shows the Stolt migration formula. I'm not going to take you through all the details. What is going on here is because Stolt migration can give us a source and the experiment at depth, so we can arrange the Stolt migration to give us an image with subsurface offset. And here, this equation, the Stolt migration image with subsurface offset. And here, Kx and Kz is the Fourier conjugate of the x and z. And Kh is the Fourier conjugate of the subsurface location, subsurface offset. And for a single reflector, we have an analytical expression from Yoon, Jedesky, and Fest. And here this shows the analytical expression for the reflection data. And we can compare this reflection data with the Stolt migration formula. We can end up with the equation at the bottom, which gives us the ability to retrieve the plane wave angle-dependent reflection coefficient from Stolt migration. Next, I will show you how can we retrieve the angle-dependent reflection coefficient from Kirchhoff migration. As I mentioned in the previous slides, that the Kirchhoff migration is a asymptotic approximation of the Stolt migration, but it loses the ability to predict a source and receiver experiment at depth. So in order to interpret the Kirchhoff migration with the source and receiver experiment at depth, we have the first approach here, which is first we interpret the Kirchhoff migration as if it's a subsurface experiment, and then due to causality, we can we can have the Kirchhoff image with subsurface offset, which is equal to 0 when x-axis is not equal to 0. And now we have an interpretation of the Kirchhoff migration of the subsurface, of the experiment at the subsurface. And we can now use the same equation to retrieve the angle-dependent reflection coefficient from this Kirchhoff interpretation. And next, I will show you the first test, which is to retrieve the angle-dependent reflection coefficient from Stolt migration and the Kirchhoff migration. The first approach. And here shows the model. Right? Oh, I'm sorry. Thank you. Here shows the model. We use a one reflector model. And this chart shows what we use in this numerical test. The data we use here is we use the data, the exact data that the algorithm requires. For Stolt migration, we use reflectivity method. For Kirchhoff migration, we use the Canyard-Hook method to generate the data. And as we discussed, the Stolt migration can naturally give us an image with subsurface offset, which is shown here. However, this Kirchhoff migration cannot naturally give us an image with subsurface offset. So we interpret by the first approach to give Kirchhoff migration an interpretation with subsurface experiment. Then we use the formula to in the previous slide to retrieve the angle-dependent information. And this slide shows the results that we get from Stolt migration and Kirchhoff migration. The figure on the left shows the real reflection coefficient for the reflector, which we can calculate from the model. And here different angle is the angle for the reflection coefficient is determined by the kx and the kz, which is the horizontal and the vertical wave number. And the different color shows the represent for the different reflection coefficient. For red shows the small reflection coefficient, and the blue shows the big reflection coefficient. And the figure in the middle shows the Stolt migration result. You can see the angle-dependent reflection coefficient retrieved from the Stolt migration are quite similar to the real plane wave reflection coefficient. Although you might notice that there are some numerical artifacts here. That is due to due to the instability at the small kz. And the figure on the right shows the Kirchhoff migration result. And we can say it is not give us nothing, but it's not as good as the Stolt migration. which is Claerbout III. And next, I'll show you another approach, which is a geometric optic approach, which we can use to retrieve the geometric optic and approximate angle-dependent reflection coefficient from Kirchhoff migration. Here, this formula shows the Kirchhoff migration equation. It's a summation. It's an integral over xs and xt, which is source location and receiver location. However, for each image point and for each source and receiver location, we can use a geometric optic picture to calculate the incident angle and if angle. And here, gamma is the incident angle and alpha is the if angle, and the c and eta were tangent of these angles. And we can change the integral of the source and receiver location to a new integral of the incident tangent of the incident angle and the tangent of if angle to rearrange the Kirchhoff migration in this formula. And after that, we can take the integral of that formula to get a Kirchhoff image with incident angle. Here, this angle is the geometric optic incident angle. And this equation gives us a way to retrieve the geometric optic approximate angle-dependent reflection coefficient from Kirchhoff migration. And next, I will show you a numerical test that retrieve the angle-dependent reflection coefficient from Stolt migration, which will give us the plane wave reflection coefficient, and the Kirchhoff migration, which in the second approach will give us the geometric optic approximate reflection coefficient. Here is the model we use. It's the same model with one reflector. And here shows the elements we use in this numerical test. It's the same like the first numerical test. The only difference is here, instead of interpreting the Kirchhoff migration as a subsurface experiment, we use an geometric optic approximation to make the Kirchhoff migration a function of the incident angle. And then we can retrieve the geometric optic approximate reflection coefficient from Kirchhoff migration. And here shows the result. Here the green line, which shows the true reflection coefficient, which is the plane wave reflection coefficient. And the blue line, which is very close to the green line, gives us retrieve the plane wave reflection coefficient from Stolt migration. You can see they are quite close. And the red line shows the Kirchhoff migration approach 2, which gives us a geometric optic approximate reflection coefficient. We can see this geometric optic approximation is not give us nothing, but it is not as good as the plane wave reflection coefficient. And next, I will show you another example to show the difference between plane wave reflection coefficient and the geometric optics approximate reflection coefficient. Here is another model we use here with different velocities. And here shows the reflection coefficient, shows the plane wave reflection coefficient and the geometric optic approximate reflection coefficient. Here for this reflector, the blue line shows the actual plane wave reflection coefficient, and the red line shows the geometric optic approximate reflection coefficient. We can see they have similar shape, but the amplitude is different. Next, I'll discuss a comparison for Kirchhoff migration and RTM for single source and receiver. We can see the figure on the left shows Kirchhoff migration for the source and the receiver location. And here, it produced candidates on an ellipse. And the figure on the right shows a RTM image with the same data, with the same source and receiver location. And this image also gives us an ellipse. And we can see the Kirchhoff migration and the RTM share some behavior, and both depend on the summing over all possible candidates. And we can see that from this example, we can see Claerbout III can provide a physical experiment at depth with meaningful amplitude and definitiveness that the Kirchhoff migration and RTM cannot provide. And we can retrieve the real angle-dependent reflection coefficient from Claerbout III. Thank you.
Yanglei showed is Claerbout III in one-way wave versus Stolt. If you look at the integrals in the Stolt migration, if you do stationary phase on one of these kg, ks integrals, you get travel time output, yes, summing over travel time, which we call Kirchhoff. And so in this talk, there's one imaging principle, Claerbout imaging 3, and its asymptotic form, which is Kirchhoff being compared. After lunch, Yanglei will make a comparison, similar comparison between Claerbout 2 and 3, two different imaging principles for the same reflector. Then we'll talk about what does Claerbout 3 talk about imaging primaries and multiples, and then how do we see the use of multiples as they are progressed, and where do we see that within our big tree now? We're going to see a new tree. As I said, we call it the Nizar tree. You can tell Nizar, we call it Nizar Chimingli. And so you'll see a new tree, which is recognizing that work, and where we see the value, within the big picture. So that's basically where we're going.